we've talked about the electron and how it can have wave-like properties or particle-like properties. And with Heisenberg's uncertainty principle, we learned that we cannot know both of those pieces of information at the same time. Okay, momentum is referring to the wave portion of it, okay, energy, and the position, that's the particle-like nature. And Heisenberg's uncertainty principle basically says if we know and can essentially pinpoint the wave portion of the electron, the particle portion of it changes. Okay, if we pinpoint the electron where it is in space or on the atom, we lose all of the other information about it. So what's the point of pinpointing one of these pieces of information? Okay, it's pointless. It doesn't give us any information. Schrodinger comes by and he actually develops an equation, mathematical equation, this is the equation I've been referencing, that describes both the particle and the wave parts of the electron. Okay, so now Schrodinger basically puts these two together and says mathematically, what can we do with it? He calls his equations, they're called wave functions. Okay, and they are given a Greek symbol called psi. So that's psi. And essentially, I'm not pronouncing the P, I'm just saying psi. Okay, if you want to draw it, that's how I usually do it, with just a U with a capital I through it. Some people like to get fancy and get kind of an upside down horseshoe type symbol, you know, whatever works for you, or make something up. Wave functions here are psi's. They describe the energy of the electron, so the wave component, and the probability of finding an electron, so the particle component. I've also mentioned this before, that Schrodinger's equation can be solved exactly for hydrogen. So just like Rydberg's equation, we can solve it exactly for hydrogen because it only has one electron. Once we introduce a second electron or even more, we cannot solve Schrodinger's equations exactly. Okay, we can make assumptions so that we can kind of reduce the math that has to be done, and then we can solve it. But without these assumptions, we cannot solve Schrodinger's equation for more than two electrons. Two or more electrons. Okay, that the interaction between the two electrons just can't be solved. So what's kind of the point of all this is we're trying to figure out where is the electron on the atom. And we know that once we find where it is, okay, we also need to take into consideration also the energy component. We need that wave component in there as well. And what we end up with is something called electron density, which is our way of saying, okay, the electron's going to be found in this certain area most of the time. Okay, there is a chance that the electron won't be found there. It could be found, beyond Pluto, but most of the time we should find the electron in this certain area. When we look at these areas of electron densities, we find from Schrodinger's equation that there are certain kind of shapes almost that happen that the electron is going to be found, and we call those atomic orbitals. And when we say orbitals, we're not thinking of like the planets orbiting the sun. So it's not this circular path, or it's not this figure 8 path. It's just an area that has a, say, spherical shape of most likely being able to find the electron. Okay, and these atomic orbitals, although we're talking about giving us a location of the electron, okay, we're not actually pinpointing the electron, we're just saying a general location, but these atomic orbitals also contribute or add or have in them the wave-like path of the electron. Okay, and this wave-like path is important to keep in mind because this is where we have an electron getting from point A to point B without ever existing in between. Okay, remember, the only way for a particle, something that has mass, to be able to do that is to behave like a wave. Okay, so on the atom, the electron is still behaving like a wave, but we're using these atomic orbitals, which represent our electron density, of where we are most likely to find the electron. So in order to describe these atomic orbitals and kind of where we should find the electron, we have a set of quantum numbers. There are 4 quantum numbers. Okay, we have the principal quantum number, and this one we used in Bohr's atom, and that's the lowercase n. And that was where we had the shells, the circular shells of the atom on a previous page. So here was our quantum number. Excuse me. We also have the angular momentum quantum number. This is given the symbol of a lowercase l. And I get in the habit of using a cursive L. So my L's are going to look like that. That way it's easier to distinguish between ones and L's. The angular momentum quantum number tells us the shape of the orbital. We are going to have 4 different shapes, really 3 different that we're going to focus on. The direction of the orbital kind of doesn't really make sense. Don't really, when you're trying to picture things, it'll make more sense when we talk about it. But that's the magnetic quantum number, and that's m with a lowercase l as a subscript. So this would be ml. And when we read this, we would say this is m sub l. Our electrons can have 2 different spins, roughly spin up, spin down. You could also think of it spin clockwise, spin counterclockwise. But this gets m sub s, and that would be a lowercase s there. All right, so in the next video, I'm going to go through each of these quantum numbers and discuss what they are, what they mean for us, and what potential values are available.